here, so it's not by the fan.
So it's been a great week for us. For Starter Mission and the whole of Kerala, the week started by us launching our Super Fab Lab, which is a $1 million USD lab with ultra modern machines which we were all amazed of. I think the guys have been spending 10 hours every day at the lab after that. And so this lab has been set up with a partnership with MIT's Center for Bits and Atoms, of which Professor Gershenfeld is a director. So he's been helping us set up labs. The first Fab Lab here was also set up by MIT CPA. We've gone ahead to set up a network of 20 labs after that. Now we have a super lab with which we'll probably start making machines and setting up more labs. So talking about Professor Gershenfeld, so MIT CBA, the Center for Bits and Atoms, does a lot of research on how to convert data into things and how the objects populate the data back. So the boundary of physical and data is what is being experimented with, and lot of interesting research. I think Professor Gershenfeld will speak to you, explain to you the research that happens there. And welcome to the session. Over to you.
I don't think I do. So I will talk for a half hour or so, 45 minutes, and then do conversation. The real goal is to explain this picture behind me. What is a super lab? Why are we here? Yeah, if you want to use that, then there's a wireless one, right? Okay. Good. Does that make a difference? I don't hear anything.
We can hear. Can everybody hear?
Is closer still?
Yeah. Now it's the
Okay, good. So I want to explain what this picture is, why I'm here. Does anybody recognize that graph? It's the most important graph in history. It's 5 data points. And Gordon Moore noticed they were doubling, and he wrote an amazing article, and he said, what happens if this would continue for a decade? Come on in. So he took 5 data points and he made a projection. What if this goes on for 10 years, was his forecast. In the middle is 50 years. That's what actually happened. It wasn't 10 years, it was 50 years. That's the only mistake he made. He got everything else right. The reason I'm here is the bottom graph is Fab Labs, these digital fabrication labs. That's 10 years of Fab Labs doubling. It's more data than Gordon Moore ever had. And so what I want to talk about is what happens if this also continues for 50 years. We're 10 years into it. What does it look like for 50 years? So MIT invented computerized manufacturing in 1952. This was the first computerized milling machine. And it grew out of this. MIT had developed the first real-time computer called the Whirlwind. That was the birth of modern computer architecture. And jet aircraft were just emerging, and there were parts you couldn't make by hand. And so somebody had the idea to connect the first real-time computer to a machine to make parts. So that was the birth of computerized machining. Ever since, pretty much everything that's descended from that has that structure. There's a computer controlling a machine. But the information is in the computer, not in the machine, in a sense. The materials are analog, the computer is digital. CBA was created to really study what happens when you merge the bits and the atoms, digital and physical. And so over the years, we've done stuff like the first quantum computation. We were part of creating synthetic life. We were part of starting Internet of Things. All of these things came at the boundary of digital and physical. And these are students who worked on it. One of my students built and ran all the computers at Facebook, and one built and ran all the computers at Twitter. And that's because to do that, you can't believe in computer science. You can't believe software is unrelated to hardware. You have to take megawatts and billions of dollars and make information out of materials. And so to do that research, we needed a facility that could go from digital to physical and physical to digital across scales. Traditionally, it's separated by different disciplines and different length scales. And so we put together roughly one of every machine to make anything in the lab we run at MIT. And I had a problem, which is it would take a lifetime of classes, traditional classes, to learn to use the machines. So I started a class called How to Make Almost Anything, aimed at a few research students. But every year, hundreds of students would show up to take it and do the most amazing things. So this was Kelly, a sculptor, no technical background, and this was her semester project.
Hi, I'm Kelly, and this is my screen body. Do you ever find yourself in a situation where you really have to scream, but you can't because you're at work, or you're in a classroom, or you're watching your children, or you're in any number of situations where it's just not permitted? Well, Screen Body is a portable space for screaming. When a user screams into Screen Body, their scream is silenced. It is also recorded for later release, where, when, and how the user chooses.
Going into the main building of the second floor.
Let's see, this is a web browser for parrots. This is an alarm clock you wrestle with and prove you're awake. This is a dress that defends your personal space. Every year, students would do the most amazing projects like that. Now, you can laugh and think that's a little bit silly. Now we'll talk about business. But MIT's Whirlwind, that was the, come on in, come in, don't. MIT, there's room further up. MIT's Whirlwind, that was the first real-time computer, was transistorized at MIT's Lincoln Labs. That was called the TX. That was commercialized. That became digital equipment. DEC's computers were used to create the internet. This is the founder of DEC, famously saying, nobody needs a computer at home. And pretty soon after, DEC was bankrupt. So when computing became personal, rather than computing for inventory and payroll, it became a personal tool. And these things back here that look silly really are answering a question I didn't ask. I did ask how to digitize fabrication. I really didn't ask why. And they were really showing that the killer app for digital fabrication, like digital computing, is personal fabrication, which isn't mass production of mass markets. It's things for a market of one. It's local production. And that may seem silly and funny, but it's an idea that destroyed the whole mini computer industry when personal computers came. So you can think of my lab as $10 million machines we use for research. $10 million machines we use for research on like quantum computing. Within that, there's a workshop of 10 $100,000 machines we use to make the research instrumentation. Within that, there's a workshop of 10 $100,000 machines we use for rapid prototyping. And then with those, you can make $1,000 machines. So motivated by that hierarchy, we did an experiment. There's one planet Earth. There was one computerized machine in 1952. There was one Whirlwind computer. Then this is the DEC PDP that was the commercial version of the Whirlwind. And this is one of my favorite pictures. This is Ken Thompson and Dennis Ritchie at Bell Labs inventing Unix. This is where modern operating systems happen, when a computer wasn't personal, but it came down to the size of a work group. And so inspired by that, we started the idea of Fab Labs. So a Fab Lab is about the cost and complexity of a mini computer. They're both a few tons, they cost $100,000, they fill a room. And rather than tell people what we're doing, we thought we would show them. So this is what was in a Fab Lab. It includes a 3D printer, but it includes all the other machines you need to use to do digital fabrication. And with them, you can make all of this. This wasn't done in a business. It's not done at MIT. Come on in. It's done in a community lab using those tools, boats, bicycles, furniture, consumer electronics. And this is what happened. We set up one of these in inner city Boston. That inspired one through a local connection to Ghana. That inspired one in South Africa. That inspired one in India. And every year they started doubling. And so there's now a few thousand of these. In fact, one of the real inspirations was Vegan Ashram in Kabul outside Pune, which is a wonderful sort of science school for dropouts that helped really convey to me that they knew what they needed to do, but they needed the tools in the field, not locked away in labs. And so we've had this exponential growth of these Fab Labs. These are just some of them. This is one in Detroit working with at-risk youth. This is Bhutan's prime minister. This is a lab working on gross national happiness, not gross domestic product. This is at a mixed community in Israel. This is an Arctic lab with Alaska natives. This is an arts colony. This is Protestant Catholic boundary in Northern Ireland. We didn't pick all of those. They all picked us and pulled these labs to those places. So to keep up with that, one of the things we had to do, like the class at MIT, is bright, not just kids, people of all ages would show up in these labs, learn skills way ahead of local schools, and then fall off a cliff. So we started a program called the Fab Academy, and the way it works is very different. MIT is like central processing. You go there for a class. Online classes are like time sharing. You're still the central computer. The Fab Academy is distributed. Students have peers in a work group with mentors in the lab, locally with machines, and then you connect them globally with video and content sharing. And so here's an example of homework in it. This was a student in a lab outside Barcelona, and he was interested in food. So all he could do in the beginning was make a sketch of an aquaponics system. Then he's learning CAD, so he's modeling it. Then he's learning laser cutting, he's making a small prototype. Then he's learning large format machining, he's making a large prototype. Now he's doing the plumbing. Then around here, he's learning to design electronics and make PCBs and program microcode. So here's his Aquaduino to control the aquaponics system. And he puts it all together. And then I love this picture. Around week 16, he's eating his first lettuce. And this isn't a work group, it's not a team, it's not a startup. This was just homework and one person learning all of these skills to go from digital to physical. And so that experience has inspired a bunch of things. This is Barcelona's mayor. Barcelona has fabulous design sense, but over 50% youth unemployment. A whole generation can't work. And so Barcelona's mayor started a 40-year countdown to urban self-sufficiency, to the idea of Barcelona producing what it consumes. And it's not a step. Every year the idea is to produce a little more. It's not protectionism. They want to be, instead of products coming in made far away and trash going out, they want data to come and go, but things to stay. These are a bunch of other cities that have signed this Fab City initiative. This is a lab we ran at the White House with Obama, and that led to this legislation.
I'm United States Congressman Bill Foster, and I'm one of the few members of the United States House of Representatives who was a scientist before entering politics. So I often tell people that I represent about 1/3 of the strategic reserve of physicists in Congress. But when I came into work each day in physics, my first stop often wasn't to my office computer or some meeting, but to the laboratory machine shop to check on the progress of some parts that I designed for an experiment or for part of an accelerator. So I believe I can safely say that I'm the only member of the United States Congress that knows how to program numerically controlled machine tools. I'm proud to announce that I recently introduced legislation in the United States House of Representatives which supports the goals and mission of the National Fab Lab Network as in the best interest of our people and the best interest of promoting the goals of greater science and technical education, greater access to research and production tools, and empowerment of individuals to understand and use technology to improve their lives. You can think of the NFLN as a new kind of national lab in the United States that's a cloud laboratory, a national network of connected local labs. I've been lucky to have the chance to visit Neil and see.
So we have a notion of universal access to, in the US, as a legislation to communication and computation. This is now chartering in the national interest universal access to digital fabrication as a kind of right. That this Barcelona project is saying consumers should become creators. Urban infrastructure isn't just roads or lights, it's the means to create. And this is chartering that in national interest as a national initiative. One of the interesting things that's happened is this is a series of companies like Airbus, Dassault, GE, Chevron, that have been making commitments against this as part of their corporate social responsibility, that they're investing in the communities they work by providing these labs, not in isolation, but as part of this global network. Once a year, this whole network meets. It was in Egypt last year. It's coming up in Montreal this year. To keep up with that, we spun off a nonprofit Fab Foundation. There's a community Fab Labs IO portal. There's a whole ecosystem of organizations that spun off to support this network. So to keep scaling, there were thousands of mini computers, and that's roughly the number of cities. And in the same sense, today we're at a few thousand Fab Labs, and so it's roughly one per city. Like there's one in Trivandrum, one in Kochi. Computing then went to here. So this was the Altair. On the Altair, the killer app was, when it first came, you could flip switches to load a binary program, and then it would run and the lights would blink. And that's what it did. And this started Micro-Soft. They eventually took out the dash. This started the Homebrew Computer Club that became Apple. This was not useful, but it was personal. And so in the same sense, we started looking at rapid prototyping of rapid prototyping, how you use the machines to make machines. And so this is Nadia and Alan. And this was a tool they made which fits in a briefcase's carry-on luggage and has an interchangeable head that can print or cut or mill. Some of you may know what a shaper is, the tool that just came to the lab here. That's Alan created the company that makes shaper after doing this. And so this was an example of a little fab facility in a briefcase. And so Alan started Shaper. One of the students who worked on that started Form Labs. You have that here. Shopbot, Bantam Tools, Fablight. These are all companies that spun off from this project to do rapid prototyping. But in a sense, you could view that as a success. Like Form Labs is now worth $1 billion. But in a sense, it's a failure because you still have to buy the machine. That wasn't the point. And so what we really want to do is you go to the lab to make the machine, not buy the machine. And so it was too hard to reproduce the machines like I showed you. These machines are complex designs, and you have to design the whole machine to do anything. And so the way we make machines has evolved. So this is work of a current student, Jake, where you start with modular machine parametric designs that let you design degrees of freedom. And then instead of having a fixed controller that does one function, it's like the internet. The machine is a real-time network. And then you make virtual software graphs of the intelligence of the machine that you overlay on the hardware of the machine. So it's modular hardware overlaid with modular software. So you might want to print or cut or have 3 or 4 or 5 axes. And this is really object orientation. All modern software is object-oriented in software, but it's now object-oriented hardware to make it easy to do rapid prototyping. So in the How to Make class I teach at MIT, 1 week we do a sprint where each of the groups of students builds a machine, and generally these are beginners to machine building. And so this is an example of one of the groups of beginners to machine building, the project they did in 1 week.
When I first gave the apple to Adam, I didn't.
Sorry, the level was low on that.
When I first gave the apple to Adam, I didn't realize how successful and innovative of a company Apple would become. After thousands of years of stagnation in the apple fabrication industry, I'm excited to announce the introduction of apple strudel.
For thousands of years, man has grown, harvested, processed, and consumed apples in much the same way. Here at Apple, we hope to change that. By over-engineering the simple task of cutting an apple, we open up a new design space for human-apple interaction.
Using the most advanced technologies available to us, including 3D printing. We were able to precision engineer a system that will last for generations. You will be proud to send it to your child when they go to college so that they can feed their friends apples.
With Apple, you know that every apple is unique. We created an interface that allows you to define your own unique apple dimensions and then carve it to the fruit of your imagination. You can define the apple height, diameter, and then have two molds to draw your perfect apple. You can use sines and cosine, and in the hand-drawn mold, you can just let your imagination go wild. Then all you need to do is generate your path, hit start, and off.
One of the hardest things about this problem that we've been tackling is how to get the apple into the computer. Now, computers aren't made with an Apple port. Some computers have Apple logos, but have you tried to put an Apple into the computer before? Yeah, many have. To get the Apple into the computer, we use a dynamic loop system known as Squidworks. That's pretty much all you gotta know. Squidworks will take care of the rest. No concept is time. You don't have to forget that. Speed. It's all just speed.
In our design, we made sure that our machine would be not systems. First, the user loads the apple onto the machine where it is called speed. Then, when the customer uses an interface, they can sculpt and design the apple as prepared. All that's left then is to send the design to the machine, where it will be used in a very accumulated way.
Besides the creativity aspects of this technology, there are considerable health benefits as well. An apple a day keeps the doctor away has been in our vernacular for thousands of centuries due to apple's demonstrated benefits on cardiovascular, neurological, and respiratory health. You don't need health care when you have Apple Care.
For our more well-off clients, get the Apple Wrench accessory. It's beautifully crafted to make sure that changing manufacturers is very easy.
Apple strudel, grown by nature, harvested by man, sculpted by machine. This changes nothing.
So that's fun and silly. On the other hand, everything you saw was done in 1 week by relative to beginners to machine build. And so it's not just rapid prototyping, it's rapid automation. If you think about what they did, it's actually a fairly complex design system, control system to make a machine. Somewhat more seriously, building on that same technology base, we're working with a National Institute of Standards in the US that has a national initiative for advanced materials. Lots of industries depend on advanced materials, but participation in advanced materials requires inaccessible instrumentation to develop and test and process the materials. And so we're doing something much like the Apple strudel, but for material science instrumentation to do open material science. And so that comes to this super lab. Thanks to Tom, the team here, Jay, Dr. Gopinath, your IT secretary, really thoughtful vision in Kerala is the goal is to expand access to digital fabrication for all the reasons I'm describing. It's to start businesses and to teach and play and do art. But to make it cheaper, you need to make it more expensive, meaning to make, instead of $100,000 labs, $10,000 labs, you need the means to create the $10,000 labs. And the point is not to import them from China or far away, but do it locally. And so with the vision of the local Kerala group, it started a few years ago with a few fab labs in Trivandrum and Kochi, built up the experience of the team here, then started a first round of mini labs. And based on the success of that experience, this is now the $1 million lab with the $100,000 tools. So each of these machines is enough to buy a fab lab. But to justify their existence, each of these, there's sort of a recursion that the fab lab can make a machine, but it can't make the parts of its own machines. These are the kinds of tools you need to make the parts of those machines. And so it's a state-of-the-art rapid prototyping lab. Yes, come on in. Walk faster, not slower. It's a state-of-the-art manufacturing lab, and you can use it for a range of purposes. Water jet cutters and large format cutters and pick and place and analytical instrumentation. About 2/3 of the machines are there, print farm. But really the core driving vision of it is for universal access to digital fabrication for everyone, to have the means to do the machine production here, at scale in Kerala. So it's a really bold initiative. A lot of parts of the world are following that experiment. The next one of these we're doing is in Bhutan, which is based on gross national happiness, which doesn't mean they're happy, but it means they measure well-being, not economic output. And many other parts of the world are following this exciting project. There are plenty of challenges. This was the import certificate that we painfully got, and this was Yahoo when we finally got the import in. But working through that, we've opened it this week, and we're having a boot camp of the instructors in the Fab Academy to inaugurate it. So that's what's going on here. Now, to go further, computing became personal in the PC era. And here there's a problem in scaling, which is a fab lab can make almost anything, and the super fab lab can make the fab lab, but this is the inventory, and this is a blow up of the DigiKey part. You need a global supply chain, not for the machines, but just for the inputs, the components to it. And so just for electronics, there's hundreds of thousands of different types of parts, but inside they're only made out of a few types of materials. And so we started studying how to code construction. So instead of, think of it as Lego bricks, but micro Lego, all of life is made on a small set of molecular building blocks. And so we started developing not printers or cutters, but assemblers that assemble micro building blocks to build technology. And so the goal is to reduce the supply chain of what goes into the fab lab to a small set of building blocks. We then started studying making those bigger to make high performance structures. And so we developed robots that take these discrete building blocks and assemble them to make high performance structures. And this is work with groups like NASA and Airbus to make world record ultralight high performance structures that you can robotically assemble. And this was a project where we then made, this was a small test one, and then we made large morphing airplanes that can change shape by assembling them, not with tooling the size of the airplane, but just using these micro building blocks. Now, ultimately computing got up to this stage. So there was one of these, 1,000, 1 million, 1 billion, there's now 1 trillion Internet of Things devices. And the Nest thermostat has the capabilities of the whirlwind computer. And so ultimately we're looking at 1 trillion fab labs. And that doesn't mean 1 trillion room-filling machines, it means the capabilities. And so to get there, this graph plots the number of parts you can place and how fast you place them. And this is state-of-the-art manufacturing, and this is molecular biology. Molecular biology is orders of magnitude ahead in its ability to manufacture. So part of what we do is program biology. We're part of creating synthetic life by designing a cell and programming biology. But that's limited to biological materials. The core part of the furthest part of this research roadmap is in biology, the code doesn't describe the thing, the code becomes the thing. The code turns into the shape. In the same sense, we're studying how to code construction of functional systems. So this is an assembler that assembles parts of machines that can make an assembler. So what it's doing is it's a cross between a 3D printer and a pick and place. It's taking micro parts, and what it's building is a little micro robot that you can then use to make more machines. And so it's almost, this is a little micro walking robot, and we're adding end effectors now so those can make more of the robots to really make a self-reproducing system. And what's interesting about that is the founder of computing, one of them is John von Neumann, one is Alan Turing. The last thing they both studied is manufacturing, and most people don't know that. Von Neumann studied a constructing automaton, a machine that can communicate a computation for its own construction, a self-reproducing system. The last thing Turing studied was morphogenesis, how genes give rise to form. That was theoretical, but we're at a point where we can really do it. And so ultimately we're studying how codes become things. As part of that, we have to learn how to design like biology does. This is a project where instead of designing mechanisms, we actually grow them and they evolve in the way biology evolves. These systems are too complex for you to design them in a CAD tool. You actually need to grow designs by building worlds they function in. And so there's a lot of attention to AI right now. Just in about the last year or so, the complexity of a large computer matches the complexity of a brain. And so it shouldn't be surprising that they can do roughly what a brain does. But we're 8 orders of magnitude off in the complexity of a person to manufacture compared to state-of-the-art manufacturing. And so this research is ultimately aimed at closing this orders of magnitude difference in the power of life, not just to think, but to create, literally breaking digital to physical. One more way to think about this is, this was a program we did for the movie The Martian on how to bootstrap a civilization. And this is asking what are the minimum technical building blocks to create a functional civilization. This is a book where I talk about all of this. My younger brother ran the biggest video game studio. My older brother ran the National Labor Relations Organization, looking at what are the social implications of access to all of this. And so stepping back, there's one Earth, 1,000 cities, 1 million towns, roughly 1 billion people, roughly 1 trillion things. Computing went through each of those stages. And now digital fabrication is going through each of those stages. But they're not happening in series. They're all here today. But this ranges from today to 50 years in the future to finish this roadmap. And we're right in the middle of this. We're right at the transition from mini computers to hobbyist computers to personal computers. And the reason why Kerala is so important, so interesting as a partner in it is to get to this next stage, you really need to embrace not providing access to the tools, but the tools creating the tools. And that's the investment happening here. And it really changes everything. It changes what is a business, it changes what is education, many foundational things in how a society functions. And so the core of the project is the technology you're investing in and what you're going to create with it. But around that is kind of this meta project of if anybody can make anything, how do you reinvent, how do you live, learn, work, and play? So with that, thank you, and I'll be happy to take questions.
Yeah, take a few minutes to digest it.
So you spoke about Fab Academy.
Yeah.
So is that something focused in each of the cities that you spoke about?
So we backed into it. The way that worked is, just to give a little context, almost everywhere there's a desire for innovation and knowledge economy, all of that. And then all over the world, programs are created to prevent it. So bright, inventive people don't like following a lot of rules and doing rote learning and doing tedious jobs. And so we found when we started creating these Fab Labs, the bright, inventive people who everybody wants would come to the lab as refugees from oppressive schools and oppressive businesses. So we would teach them skill, we would start teaching them, but they would kind of fall off a cliff. Where do they go next? And so we started the Fab Academy to help keep up with their education. And so first, the Fab Academy, which I'll tell you about, is now one of a group of classes. It spawned a Bio Academy for biotechnology, a Fabric Academy for textile technology, a whole group of classes. The core Fab Academy teaches the skills of digital fabrication, just like the class I teach at MIT. The skills to go from digital to physical. We didn't push it. We started beginning to do this, and more sites opt in. So right now, about 100 sites participate. Each is a well-equipped fab lab with a skilled instructor and a work group of students. And there's a weekly cycle of, I give a global video lecture that's interactive, then students go off and work in the lab for the week. And then we connect in giant few hundred site video conferences where we discuss everybody's experience and then progress to the next unit. Work up through those individual units to final projects that integrate them. And then once a year, this whole community gathers at the global fab events. And so it's this distributed educational system. Maybe one of the most interesting parts of it is we had to create our own accreditation because there is no accreditation that covers this. But now many well-known universities like the Sorbonne in Paris recognize our made-up accreditation as theirs. So their students do this and they get our training and our credential, but at the same time they get the certification from the Sorbonne. And so they're overlaying our accreditation on their accreditation. One more thing we're going to be trialing at Kerala is the Fab Academy really trains the trainers. It's this intense global class. We're spinning off a version that's much slower, covers the same material, but much more slowly in local languages and local time zones, calling it Fab Academy X, and we're going to be trialing a version of that in Kerala.
So, when will we be looking at lithography and thin films?
At the what?
Lithography and thin film for manufacturing.
Hopefully never. And I mean that quite literally. So there's a precocious high school student, now college student, who I've gotten to know, who made a chip fab in his garage, literally. The research I'm showing you is aimed at completely avoiding chip fabrication. And so to say that carefully, chip fabs today are a multi-billion-dollar investment. It's a very high barrier. And the turn time for a state-of-the-art chip is a year. Yeah, it takes roughly a year to produce the chip. It's just broken. And so there's a low end and a high end. One of my students recently did a very successful thesis, and he now has a startup working on direct write MEMS fabrication. But the MEMS fabrication doesn't use lithography. It's based on laminating with the direct write process. So you can turn it into a tabletop way to produce MEMS without lithography or thin films. We're part of a project with DARPA in the US, where there's a national initiative. US is kind of losing its ability to make chips. They rely on global foundries, and it costs $100 million for a state-of-the-art chip, and again, it takes a year to develop it. And so we're developing new ways to make chips based on microassembly. And so if you go back to this graph I showed you, state-of-the-art manufacturing is in here, molecular biology is up here. Molecular biology only uses a tiny set of building blocks, 20 amino acids, and codes their construction. So in the same sense, in this DARPA project, what we're studying is ways to make 3D integrated electronics by microassembly, completely avoiding lithography and thin film. And so the research roadmap is aiming to skip over that stage to really scale exponentially.
Look at the fabrication.
Little louder.
The fabrication machineries that we are having here.
Yeah.
So when you look at fabrications which are happening in the industries, mostly they use multi-axis printing machines, laser cutters, metal laser cutters and others. So how can we go into that particular level from this lab?
So first, let's see, just a general comment is we, both my lab at MIT and the Fab Lab Network, have had great collaborations with large companies looking 50 years in the future, like say Airbus. And we've had great collaborations with new startups creating businesses. To understand that, just as a footnote, MIT, the businesses spun off from MIT fall between the economic output of India and China. It's trillions of dollars a year. It's the world's 10th economy. And it doesn't come from trying to get rich. It's driven by vision of what new technologies can do. And so on the other side, we've done lots of business creation. There's been a lot of frustration working with mid-sized companies that just want to use new tools to do exactly what they're doing and not really think about revisiting how they do things. Like this question about lithography is a good example. MEMS is important for lots of industries. It uses billion-dollar chip fabs because that's what's available. My student's thesis was how to reinvent it with a laser direct rate process. So against that background, the machines are about 2/3 here. This is a NC mill that arrived a few hours ago. Still to come is a 5-axis machining center. Let's see, I don't see it in one of these pictures. There's a fiber laser here. We may add a kilowatt fiber laser. These are the tools that the businesses use. But part of the strength of this lab is the ability to integrate them. So for example, this is a large format cutting machine that one of my students modified to do, for example, large area wire plotting, to do active electronics in a roll-to-roll process the size of a 10-foot machine. One of the strengths here is the ability to take these processes and integrate them in new processes in new ways, not just matching what the companies traditionally do. The super lab isn't a base fab lab. It has the machines. This is an injection molder. This is the pick and place. It has the machines like traditional industry does. But like, for example, this pick and place is designed, it's very high resolution for state-of-the-art limits and placing parts, and it has a vision system, so you don't need to feed parts in reels for large batches, and you can train it really quickly, so you can use it to do quick turn production without spending a day on setup. And so the lab straddles, it has the machines like traditional industry, but they all have a kind of agility, and what's interesting is ways you connect them rather than using them in isolation.
We talked about collaboration startup. So as an outsider, when I'm going to that, I will have to book each and every machine, right?
You're making a statement. You're asking a question by making a statement.
Scenario that I encounter.
Sorry?
I'm saying a scenario that I encounter. Okay. So when I go to Fab Lab, I will have to book each and every machine to use that. Okay. So
Once again, let's take turns. You're making a statement. You have to book each and every machine to use it.
Yes.
That's making a statement, but I'm not agreeing with your statement. Ask a question rather than make a statement, and then.
Yeah. So is there a long-term collaboration with the startup? So let's say for 1 year I want to use my R&D, I want to develop the product for 1 year in Fab Lab. So is there a collaboration with startups that startups can?
I think that's a question for me rather than for you.
But we'll both answer. But again, you're making a statement about how a Fab Lab works. There's thousands of Fab Labs. So
I'm asking about a collaboration.
I understand.
Startup and Fab Lab.
Right.
For 1 year. So it's really nice.
Right. There's thousands of Fab Labs, and every Fab Lab has some relationship to startups. The important thing to know about your question is asking about how Fab Labs relate to startups is a bit like asking how does a library relate to a startup. And the reason I say it that way is healthy Fab Labs incubate businesses, they teach classes, they have free open time for the community, they do outreach, they do kids programs, they create community infrastructure. There's a whole ecosystem. And that ecosystem is what makes the lab healthy, the interaction of all of those. So it's very important, I'm framing it this way to understand, the lab can indeed help startups, and they do create startups, but it's important to recognize you're joining a community using the lab that has a range of uses. It's not simply in isolation a startup vehicle.
I mean, I think you've answered for me as well. So we have all the machines, but we still need to know, this is a process of managing the lab. You're booking the machine so that others know the machine is booked. Whereas we have a process in place for everybody to book the lab and use it. And I understand that some of you might not get the machines when you want because somebody else is booked or it's used for our internal projects. But the process in place for letting you know that this machine is not available or not available.
Okay, and let me also belabor, today, this talk for everybody in the room is a punctuation mark, it's a transition point. In this era, the Fab Lab era, there was Fab Lab Trivandrum, Fab Lab coaching. And you had to fight over who gets on the laser cutter. The whole purpose of the Super Lab, the whole purpose of this initiative is, for any one of the machines on this scale, the bill of materials for them is hundreds to thousands of dollars, not $100,000. The whole goal of this lab is to not fight over who gets time on the laser cutter, but have the means to create the laser cutter locally, and not just laser cutters, but machines associated with the workspace. And so, Fab Labs have policies for how startups join in the community to help the startups, but also not displace all the other activity. But the real exercise, and the reason I'm here today, is for viral growth. We're going to go from 1,000 to 1 million. 1 million is the number of towns on Earth. It's having these capabilities in every town. To do that, we want to create the capability in Kerala to really produce at scale. And so the real goal of the Super Lab has multiple goals. One of the goals is indeed, if you start in a community lab and then you progress to the Fab Lab and then you have more advanced stuff you can't do in any of those, you progress to the Super Lab. One of them is indeed businesses wanting to collaborate on state of the art, but the real heart of it is expanding access, really making these capabilities accessible to everybody everywhere.
I have a question.
Yeah.
So to make that transition, what are the technological challenges and the innovations that we are waiting for?
I'd say the real innovation needed is less technical, it's organizational and it's social. These pictures date back to 10 years ago. We were already doing rapid prototyping of rapid prototyping. There's kind of this whole package of helping people understand the real goal is not to buy the machine, but make the machine, and rather than the machine being a scarce resource to expand access, and investing in the infrastructure, and as you've been doing, building the skills, and starting to think about how to scale and deploy it. And I had thought the technology behind all of this was hard, but that's progressing well. And there's some details, there's some next steps technically, but the technology on balance is in a pretty good shape. What's hard is this doesn't quite fit, let me go to this picture.
I'm United States.
This Fab City initiative. There's a historical equality that, like, Barcelona has 50% youth unemployment. That's a disaster. So they need to create jobs to have employment so people get money. And then with the money, they can buy things. If you go in the Fab Lab and make something, rather than jobs have money to make something, to buy something, if you make it, it's not free, it's not utopia. But if the consumer becomes the creator, it fundamentally gets at the, sort of challenges in a sense, what is a job, what is work, what is money? If the goal isn't simply money, but livelihood and sustaining life and, changing this relationship between consumers and consumption and creation is more fundamentally sort of asking what is an economy for and how does an economy function? And that's a really big, deep question that's very related to going from 1,000 to 1 million. That, if you think about when computing went through these stages, how economies changed, how we live changed. That's what's happening in the stage, and that's the part that's really hard. Figuring out what does business mean, what does education mean, how do you deploy it, how do you support it. In a startup mission, it's sort of tautological. The job is to create startups, and the job of the startups is to grow and get rich. On the other hand, to relate a few different things, in this picture of labs, this is Bhutan's really thoughtful prime minister. He gave an amazing TED talk on how Bhutan is a carbon negative country. And a while back, their king decided it was crazy for the country to be based on measuring money for deciding how good it was doing. Instead, they should measure the health of people, the happiness, the well-being, the stress. And this gross national happiness is widely misunderstood. It's actually really serious. The happiness office people are scared of because you have to report to it how you're contributing to the well-being, and you're measured on well-being, not on the money you produce. And so you can see how Fab Labs fit perfectly in that. And there's a deeper sense of the startup mission, which is sustainable innovation that transforms the community. But if consumers can become creators, it doesn't simply mean a business, the job of a business is to get rich. It's really asking these deep questions about how economies work. And that's hard. Nobody knows how to do it. Everybody's figuring it out. And kind of charting that, the technology will come, but charting that is the really kind of meta experiment here. Yeah, and let me just belabor what I said before. In a cluster like Kendall Square in Cambridge, where I work, that's created trillions of dollars a year in business, people's eyes glaze over if somebody shows up with a PowerPoint deck on their business plan and they multiply a big number by a small number to get a pretty big number to say, here's the money I'm going to make. The trillions of dollars of business doesn't come from starting with business plans. It doesn't come from find a problem and solve it. Two things drive it. One is vision of change in the world. I want flying cars, or I want desktop MEMS. The other one that really drives it, that's often forgotten in business schools or startups, is just culture. Is a lot of the business creation is creating environments, places where you want to go to work, creating places with people you like, doing things you like as an environment you want to be in. And that may sound squishy, but those are the things that really drive trillions of dollars of businesses, not PowerPoint decks with business plans. This combination of vision and culture. And that's why this is such an interesting moment, because all of that feeds into this pivot from just the job of business is business to the transformation of society and how the technology fits into it. It's really a bold, grand experiment. You should be thankful and not take for granted to have it this. So the state has been doing something really thoughtful, which is first doing these local labs, building experience with them, then scaling down, then growing up to this, but crucially not locking this away behind guards or in a academic institution, but really making it a resource for the state. It's really thoughtful. It's a really interesting experiment.
And Matthew, first of all, thank you for accelerating this maker movement. And the question I want to ask is this. We have all these fabrication facilities in Fab Lab, but I feel like the safety aspect is often overlooked, right? We are continuously printing in a small room, or we are making use of this laser cutter, all these fumes are coming out. And I I'm not sure if that is a part of agenda that this is already discussed or there's a plan for it, but somehow it is not being implemented at the scale that it is mentioned, I think.
Yeah, so that's a really important question. In shepherding the growth of Fab Labs, we worry a great deal about health and safety. So we make circuit boards by precision machining, not etching, so there's no chemical waste. We choose molding and casting materials that don't need hazardous ventilation. There's a lot of things we use to try to keep the labs environmentally friendly. But for example, to take the laser cutter example, we try to steer people away from laser cutting acrylic to using renewable materials, but can't prevent people coming in with acrylic. And then when you laser cut, if you're venting properly, you need to wait a minute or two for it to outgas. And if you get impatient and open the lid, then you breathe the fumes and the lab smells bad. And so we try hard to train people for safety, and a piece of the Fab Academy is propagating that training. But ultimately at heart, your question is a deeper one because Fab Labs let you make dangerous things. Like you could, increasingly people make cars, make vehicles in labs. And there's a century of how you regulate something like an automobile or even a bicycle. But if you make it for yourself in the lab, how do you manage safety? And so there's a number of people working on, you can't, generally all the ways we manage those things historically has been by legislation. There's a rule for how you do it. But there's too many of these, you can't legislate it, you have to provide incentives to opt in for it. And so figuring out how you sort of use that soft power to manage it is really important. Again, one of the important things the Fab Academy does is propagate those best practices to help train that. And also understand, if you go back to the scaling, let's see, I'll go to at the end. If you compare the room filling whirlwind to the Nest thermostat, the laser cutters have, they might be around for 10 more years, but ultimately the goal is to kill them off. This research roadmap for the future of Fab Labs is moving towards microassembly of functional building blocks. So not printing or cutting, but assembling or disassembling. And that has profound, among other things, environmental implications because there's no trash in biology. Forests don't have waste, you reuse the materials. One of the things driving this transition is to make fabrication reversible so you can unbuild as well as build and reuse these building blocks. And so, I view the safety issue with laser cutters as important, but only transitional as a transitional stage in this research roadmap.
In connection with that, the thing is, in our Fab Labs, there is like materials are, once the given set of materials are depleted, then we go on to buy locally sourced materials, something like a wood piece or acrylic, as you said. So is there something set up so that we can take the materials from the people who already gave us the machines and stuff, so that, like, I'm asking?
So there's two parts to your question. One is, right now there's a very active project to create a global supply chain for Fab Labs. There's a team working on exactly, from a small part up to the whole lab, how to source with a global supply chain. And so we're trying to turn that on. But there's also another part to it. There's a really good collaboration looking at, for the foreseeable future, there's a small set of high-tech consumables you have to source globally. But there's really interesting research on sustainable production using local materials. So how to make things like resins and composites and high-performance materials in a curated way out of local resources. And so there's a really interesting collaboration. The project I mentioned we're doing with the National Institute of Standards is also working with what's called Materiome, this group, on using natural resources to sustainably produce advanced materials locally, as well, not just the global supply chain, but to really revisit local supply chains. those are both important questions.
Yeah, so the fabrication and the things that is going to happen at the local level is going to increase quite a lot. As you said, in the future, you are planning to scale it in such a way that anybody can make anything anywhere. So there has been a series of enterprises, businesses, which is right now thriving in the world. Would you think that in the future it might bring a lot of disruption and a lot of scenarios like a recession or something like that into businesses?
Well, see, you said disruption and then you said recession. So the whole computer industry was outside Boston in the mini computer era. When PCs came, they were all destroyed. But what came out of that was Apple and Microsoft and a huge engine of business creation. There's no question that this will disrupt business. One thing to note is personal fabrication isn't all fabrication. So if you look at computing, you might have a computer in your watch, you might have a bigger one in your phone, a bigger one in your tablet, and a bigger one in your desktop. You might have a workgroup computer, you might have a local cloud data center. If you're really ambitious, you might use a global, there's a whole hierarchy of computing. So in the same sense, personal fabrication isn't likely to become all fabrication. There's still a role for mass manufacturing, but that's for things where there really are economy scales where there isn't value to make it different. They're the least interesting things. But in between do-it-yourself and mass manufacturing, this is going to create all these new intermediate tiers. It doesn't replace the extremes for it. But there's no question that, once again, as we've been discussing, it's going to destroy a lot of likely mid-sized businesses. It's going to lead to startup creation. We've worked with Nike on sneakers or IKEA on furniture. They're really planning to be here in 50 years, and they're really thinking deeply about how they relate to this. There's a lot of mid-sized businesses that are like this picture that think this is all toys and are likely to get blown up. But again, to come back to you said recession, this is a fab lab in a tiny village off the coast of Iceland called Vestmannaeyjar. And in that lab, these are all things made in labs that you can make in any other lab. If you make them, it's not utopia, it's not free. You could make it for yourself. A friend could make it for barter or exchange. It could be done as a local business. But if you think about all the infrastructure of producing something, shipping, selling, taxing, all of that, if that goes away with local production, you don't need a lot of the infrastructure the way the economy runs today, and you take out a lot of intermediaries in how the economy runs. And so it's not as simple as does disruption lead to a recession. It's really sort of rewiring the economy. And nobody knows how that's going to play out. And in many ways, the real opportunity is to figure out what the new business models are. Now, the last time around, the winners were Google and Facebook and Amazon. That's likely not to happen here because those were central, and this is so fundamentally distributed. Maybe a better analogy is if you think about cooking. Economies of scale in cooking are like McDonald's franchises for mass market food. And if you really want to have a good meal, you don't go to that. You go to a local restaurant that does interesting cooking. And it may be that this ends up more like local restaurants, not McDonald's franchises. And so the thing I keep stressing is don't assume the assumptions of the economy that got us to this point. This is really evolving how an economy functions and who pays who. Like one more part of it is if you take the sustainability of these fab labs, each of these has business models for how they function. But the most successful business models generally don't involve making a product and get paid for the product. They include all different kinds of benefits of making something. So remember, Google took a while to figure out they don't sell their product. They don't sell search. They give away search, but they sell the benefits of searching. In the same sense, many of these labs don't sell making. They sell the benefits of somebody having made something, which is a subtle distinction and involves really creating new kinds of business models of who pays whom for what. So I just keep repeating, don't assume, so when we take successful entrepreneurs from the last dot-com boom bust and bring them into Fab Labs, generally they're just not very useful. That the skills from the last round don't carry over to this round. There's new generations of entrepreneurs really deeply thinking about new models of who pays whom for what and how an economy functions emerging here. So maybe that's a good point to close on. So I wish you great luck. We'll visit you, teams will visit us, and understand that today I couldn't give this talk anywhere else. To say the state of Kerala has invested in a super lab for machines to make machines to transform the state of Kerala. Right now there's only one place on earth I can say that to, and it's here. It's a bold experiment, it's a grand experiment, right in your backyard. Thank you.
For me, that is really mind-blowing, all these insights, and I believe Neera's also got a lot of you thinking very differently right now. Thank you for this wonderful session, and thank you for working with us to set up this lab. As a token of appreciation, I would like to invite Yadu, who leads our Super Fab Lab, to present a small token of appreciation. Photo. Made in Fab Lab, given by Neil. Thank you for joining.